Hello, and welcome to today's podcast on the HR diagram. The learning goals for today are that students learn about the factors that affect the star's brightness. Students will learn about two ways to measure a star's brightness, absolute magnitude and apparent magnitude, and students will learn how to interpret the HR diagram. Before we begin, let's discuss two quick vocab words you'll need. Lumens. This is the unit that scientists use to describe the amount of light given off by a source. You've seen this mentioned on the side of light bulb packages. You can compare how much radiant energy different bulbs give off by comparing the number of lumens they produce. Luminosity is a measurement of a star's brightness. Astronomers measure the star's brightness by examining the amount of energy emitted or given off every second. The more energy emitted, the higher the brightness. Here are some specific factors that affect luminosity. As the size of a star increases, the luminosity increases. If you think about it, a larger star has more surface area. That increased surface area allows more light and energy to be given off. Temperature also affects a star's luminosity. You don't even need to look at a star for this idea. Just think about a stove or a fire. When you see very little light, chances are the temperature is lower. When an electric stove is off, it's black. When it's on high, the stove glows bright red. Same idea applies to stars. As the star gets hotter, the number of nuclear reactions increases, more reactions, more energy. And lastly, the distance from our eyes to the star affects how bright it looks to us. There are two ways to measure a star's luminosity: apparent magnitude and absolute magnitude. Apparent magnitude is a star's brightness as it appears from Earth. This is affected by all three factors we just mentioned: size, distance, and temperature. Absolute magnitude is the true brightness of a star, measuring how much light is given off by the star, not how we perceive it from Earth. This one is only affected by the two factors we just mentioned, size and temperature. This one is not affected by distance because it's as if we're taking the measurement of its brightness as if it were the same distance from us in space. We compensate for a star's closeness or distance in this measurement. Using absolute magnitude, you can compare two stars' brightness that are vastly different distances from us in space. Again, the apparent magnitude is a measurement of how bright the star appears to us from Earth. The candle appears to be dimmer and dimmer the farther away you move it in space. The candle's not actually getting brighter as it goes farther away. It just looks less bright because it's farther away from us. Less light is actually reaching our eyes. If you put a flashlight to your eye and turn it on, of course it's going to look really bright to you, but it's not actually any brighter than if you were looking at it from across a football field. The apparent magnitude is a measurement of how bright the star appears to us from Earth. Absolute magnitude is a measurement of how bright the star would be, regardless of its distance from us on Earth. The more negative the number, the brighter the star. So you can see on this chart that the Sun, compared to these other stars, is not the brightest. Deneb is a really bright star, as you can see, because its absolute magnitude is really negative. That's not how they look to us, though. The Sun is extremely close compared to the other stars. Deneb is really, really far away. So if you look at it in the night sky, it's not going to look as bright as the Sun, obviously. Let's check out the apparent magnitude of these stars now. It's obvious to us that here on Earth, the Sun appears to be the brightest star in the sky with a whopping apparent magnitude of negative 26.7. Remember, the more negative the number, the brighter the star. Even though Deneb is the brightest star in terms of its absolute magnitude, it appears the least bright, or the most dim, because it's so far away. We can determine a lot about a star when we look at its luminosity and its temperature. As you know, stars go through different phases during their lifetimes. The stages that a star goes through depends a lot on how much mass it has. For example, the fate of an average mass star is very different than the fate of a very massive star or an extremely massive star. If we were to plot the temperature and luminosity on a graph, we would see that these characteristics change throughout a star's lifetime, and that stars that are in similar phases tend to group themselves together on this graph. This is an HR diagram named for two astronomers, Russell and Hertzsprung. Before I start talking about the application of this graph, I just want to point out the axes. Notice that the y-axis has luminosity on it, or brightness. And as you go up on the graph, the stars get brighter and brighter. Also notice that the x-axis has temperature on it, and it's backwards. The hotter stars are blue, and they're over here. And the cooler stars are red, they're over here. Temperature actually goes up as you go this direction. It's backwards from a normal graph. Like I said a second ago, stars that are in similar phases of their life have a similar temperature and luminosity. For example, stars that are white dwarfs are compact and thus pretty dim, but hotter than it would be if they were in the main sequence. Normal hydrogen-burning stars are in the main sequence of their life. These stars group themselves together in the middle of the graph along this line. High-mass stars are blue when they're in the main sequence, and low-mass stars are red when they're in the main sequence. They're neither as bright nor as hot. This is where a sun lies on the HR diagram. It has an average mass, and it's in the main sequence phase of its life, chugging away, fusing hydrogen. Note the lifespan of the star varies with mass. The greater the mass, the shorter the lifespan. Compare Spica's lifespan, 10 to the power of 7 years, 7 zeros after that, versus 10 to the power of 11 years for these guys over here. Proxima Centauri is going to live 10,000 times longer than Spica, which is furiously burning up its fuel to counteract the intense force of gravity crushing its core. Let's do some problems to get some practice reading the HR diagram. I'm expecting you to do all 7 of these or 8 of these in your notes. Which star on this diagram is the hottest? Don't forget, the axis is backwards. So choose between A, B, C, and D. Number 2, which star is the most luminous? Remember, luminosity can be found on this axis right here. Which star is a main sequence star? Which star do you think has the largest radius? And which one is most like our sun? Number 6, which of these stars will have changed the least in 10 billion years from now? And number 7, which of these stars can be no more than 10 million years old? And that's all for today. Thanks for watching.